Now we are recording. Let's go to current slide. I'm trying to think. That's hard. Boy, the computer is awfully slow today. There we go, finally. I don't know of any major announcements except the sad one about, no school next week, so get over that one. But we will come back refreshed, or possibly, what's the past tense of spring break? Spring broke. Never mind. You wouldn't do that. Okay, so let's come back refreshed. Okay, so if there are no announcements, any questions? All right. Yeah, you're in here. My Asia's here. Okay. And anyone else coming? All right. If there are no questions, we're continuing Chapter 2, making good progress in it. Polynomial and rational functions. So far, we're still on the polynomial part. And 2.4 is complex numbers, or complex numbers. But we are just going to slideshow through this one. I'll talk about it a little bit. You're not responsible for it on a test because it wasn't in the course description, okay? However, you may run into these in the future, so I want you to be able to deal with them if you got them. And then if you do ever see them, you'll know what they're talking about. So quickly, the objectives here are use imaginary unit I to write complex numbers. We'll add, subtract, and multiply complex numbers, or at least I'll show you how to do that. We'll use complex conjugates to write the quotient of two complex numbers in standard form. Here's Siderius. Okay. All right. And finally, find complex numbers, solutions of quadratic equations. That's why we're introducing them, because some quadratic equations, when you go through the process to try to find solutions, you'll find out what we've said before, no real solutions, or only one real solution. Well, that's usually a double root. When there's no real solutions, that means there's usually at least two complex solutions, okay? So let's start with the imaginary unit I, okay? You've learned that some quadratic equations have no real solutions, like I was just saying. You draw the graph and they don't touch the x-axis. They're either above the x-axis going up, below the x-axis going down, no real solutions. But Samaya is real, okay? So, get her marked here, okay. Turning into a decent class now. Okay, size class, always a decent class. Okay. For instance, this quadratic equation here, x squared plus 1 is equal to 0. What value of x will make that true? There is no real number x that will make that true. Absolutely none. Amina, I got it. Okay. Oh, my page was crooked. I thought I'd already had you marked here, but you're not. Okay. Now you are. Okay. All right. No value of x you can put in there to make that true. You might say, well, pick an x. 0. No, 0 plus 1 is 1, not 0. Well, how about 1? No, 1 plus 1 is 2, not 2. How about negative 1? That should work, right? No, negative 1 squared is still 1. 1 plus 1 is 2. Any negative number you put in for x, when you square it, it becomes positive. That's going to be a positive number, not 0. Any positive number you put in for x, that's going to be positive, and add it to 1, and it's not 0. No real solutions. No real number x that can be squared to produce negative 1, because if you subtract 1 from both sides, you'd have x squared equal negative 1, and think, wait a minute, you square any number, it's going to be positive, not negative. To overcome that deficiency, mathematicians just created, out of thin air, a solution. And that was Dion. No, it was number I. Okay. All right. A couple of clusters running here. Okay. That thing they created, an expanded system of numbers using the imaginary unit I. And just a moment on that, let's back off and think about systems of numbers. When you first got started, probably at home, when your mom or dad or uncle or sister or somebody was teaching you to count, what numbers did you use then? They're given two names. One's a fairly obvious name, like Rhodesia, okay? Okay? Well, not even real numbers yet. Counting numbers. You counted with the counting numbers. 1, 2, 3, 4, 5, 6, 7. That had another name for it, and that name was natural numbers. Okay? TK? Yeah. Okay. So those are just the counting numbers of the natural numbers. 1, 2, 3, 4, 5, 6, 7. And you thought that's all I need, right? Well, no. Sometime or another, someone thought you needed at least one more number in that group, a really big, powerful number, 0. Okay? And what 0 did for you, that made it the whole numbers. The counting numbers plus 0 is what we call the whole numbers. And you thought that might be sufficient. No, not yet. You needed negative numbers on the other side of 0. So those are called the integers. Okay? Positive counting numbers, 0 and negative counting numbers. Those are the integers. But then at some point, you knew you would have to run into fractions. Okay? And by the time, those were then called rational numbers. So they're the ratios of any two integers, as long as that bottom integer is not 0. You can't ever divide by 0. Any other integer you can put in the denominator, any integer you can put in the numerator, that made the rational numbers. And guess what? All of your integers were rational numbers. You could just divide by 1 and you got them. Okay? Just like we got Patel. Okay. Now, anyone else know what's called wrong? So, we came up with another set called rational numbers. And the rational numbers included everything we talked about before. Counting numbers, natural numbers, whole numbers, Thomas, everything. There you are. Okay. All right. So those were the rational numbers. Surely that will be enough numbers. Fractions, decimals, whole numbers, integers, sign numbers, everything. Shouldn't that be enough? Oh, no. As soon as we learn to take radicals, square roots, cube roots, fourth roots, fifth roots, and stuff, then we ran into numbers that cannot be expressed as a ratio of two numbers. So since they can't be expressed as a ratio, they're irrational numbers. Okay. Now, finally, if you take the irrational numbers and the rational numbers, combine those together, that's what we call the real numbers. Well, those are all the real numbers. Surely we're through. No, we're not, because you can't find the solution to that with the real numbers. So they came up with this, out of thin air, an imaginary unit. And the definition of that would be the solution to this right here. Because if we were to try to solve that, if we were trying to solve that, let me get my pen set up. Okay. We would, like I said before, subtract 1 from both sides, and that would give us x squared, that goes to 0, is equal to minus 1. And then the next logical thing would be to, how do you undo a square root? How do you undo a square? Yeah, right, okay. It must be Thursday, okay. some day of the week, okay. Take a square root of both sides. Oh, and we've got a problem, don't we, Houston? This comes up x, okay, but this comes up something we do not have a number for. Square root of -1. You can't take the square root of a negative number, we've always said, right? Just like you can't divide by 0. Well, you still can't divide by 0, but now we can take the square root of a -1. And we call that I, okay? Imaginary number I, okay? And actually, this answer is not just I. When you take a square root of both sides, you have to do a plus or minus. That'll be plus or minus I. Those are your solutions, because if you put in a minus I there, square that, that would be minus times minus is plus, and I times I is I squared. And here's the other definition you need to know. I squared is equal to -1. So these two pieces of information, they really say the same thing. I is defined to be the square root of -1, and therefore I squared is -1. So now we can put in an x squared here, I squared plus 1, -1 plus 1 equals 0. So that will solve that solution. We think we got them all now, okay? We had real numbers, now we have numbers with imaginary components, okay? Now, by adding the real numbers to real multiples of that imaginary unit, I, now you have another whole set of numbers, and these are called the complex numbers. Excuse me. And that would be all real numbers and all real numbers with imaginary parts, okay? So each complex number can be written in standard form of A, which is a real number, plus B, which is also a real number, but that real number is multiplied by I. So all real numbers, all complex numbers can be written in that form. The one we just had, I, that would be 0 plus 1I. I, okay? That's a complex number. We usually don't write the 0 down, so just I is standard form for it. So, what if you had complex number -5, that's the A, that's a real number, plus square root of -9. Oh, wait a minute. Can't do square root of -9, but you can do this. Okay, very good. You do plus, you actually pull out the square root of -1 times the square root of 9. Perfect, okay? And what's the square, this is -5, and what is, that would be square root of -1 is I, and square root of 9 is 3, so then really the way you were saying it is better, -5 plus 3I. We usually put the real number in front, just like we say here, okay? So that's how we get that. And they did the same thing down here. Rather strangely, but they did it. Yeah, they pulled out the square root of 9 first, and then square root of -1 is I. -5 plus 3I. Any questions? Okay, again, you're not responsible for these on the test, but I want you to see them, know them, be familiar with them, and in case you ever need them, you won't say, he never told me. Okay, so here's the definition of a complex number. The A and B be any real numbers in the world. Rational, irrational, positive, negative, fractions, decimals, it doesn't matter. The number A plus BI is then called a complex number. And it's said to be written in standard form when you write it like that. The totally real part plus or minus the real times the imaginary unit. Okay. This here. Okay. Anyone else come in since you called off? All right. So that is what we mean by a complex number in standard form. The real number A is called the real part, and the real number B is called the imaginary part of the complex number. I don't always stick strictly to that. I usually call BI the imaginary part because that has the imaginary unit in it. But the book calls just the B that goes with BI the imaginary part. Now when B is equal to 0, guess what kind of number you got? Real. This is just a real number. So if B is 0, you got a real number. If B is not equal to 0, And here again, there's a little bit of confusion here. I call a plus bi a complex number. They call it an imaginary number, which is fine. It sort of is. To me, I is the imaginary unit. Okay, but we won't get into that. It's just semantics. Okay, a number of the form bi, where b is not equal to 0, but a is equal to 0, that's called, the book calls it a pure imaginary number. And that's a fine thing to call it, pure imaginary number, whereas if it's got a real part, it's just called an imaginary number, but to me, that's the same as complex numbers. So why use two different terms for the same thing? All right, now this, what I was talking about before with the different sets, we talked about what goes into this set. The counting numbers, or the natural numbers, add 0 to it, and you get the whole numbers. Do the positive and negatives, you get integers. Then you do rational numbers, ratios of integers, except 0 can't be a denominator. That will give you rational numbers. Then any number that can't be expressed as a rational number, like square roots, pi, e, some of those bizarre numbers, never repeat a decimal pattern. They've taken pi and all these other numbers, square root of 2, square root of 3, square root of 5. They've taken them to as many digits as the computers can establish, and they never develop a pattern. Whereas all your rational numbers will develop a pattern at some point. Irrational numbers will not. They can't be written as a ratio of two integers. So those two together form your real numbers. Down here, you just have imaginary numbers a lot. And you see here is where I think they fall apart a little bit. When you combine real numbers with imaginary numbers, but frankly, all real numbers are imaginary numbers, I would say when you combine real numbers with pure imaginary numbers, then you get complex numbers, because that's a complex number just like that is a complex number. So I think their definitions have a few gaps in them, but you get the idea. You get strictly real numbers with numbers that have imaginary parts, then you have what you call complex numbers. That's true because every real number a can be written as a complex number, it's just b is equal to 0. That is, for every real number a, you can write a is equal to a plus 0i. Who wants to write that? Just write it as a. Okay. So, what do we mean by two complex numbers being equal? These are characteristics of number sets. Two complex numbers, a plus bi and c plus di, in order for them to be equal, when they're written in standard form, they're equal to each other if and only if a is equal to c and b is equal to d. The only way they can be equal to each other. Just because, nothing. So 7 plus 3i is not the same as 3 plus 7i. Definitely not the same. 3 plus 7i would be the same as 6 halves plus 21 thirds I. Because those are the same values. A is equal to C and B is equal to D. Who would want to write them that way? I don't know. So, what operations can we do with complex numbers? What are our four basic operations? Adding, subtracting, multiplying, and dividing. So let's hit those. Start with adding and subtracting. To add or subtract two complex numbers, add or subtract the real parts, add or subtract the imaginary parts. Guess what? You got it done. You do them separately. It's, what does that look like to you? Something we've already been dealing with a lot? It looks like a binomial to me, right? Two terms, two numbers. Okay? But only one part. Okay. The one and only. Okay. Got it. Okay. Now, so when you're adding binomials, you add like terms, right? When you're subtracting binomials, you subtract like terms. So think of these as terms. That's what they are, things separated plus or minus. So you add the real parts, add the imaginary parts. Subtract the real parts, subtract the imaginary parts. Just how they're done. So the sum of a plus bi plus c plus di would be a plus c would be the real part, and b plus d, bi plus di would be b plus d times I. And the difference between two complex numbers, a minus c is the real part, b minus d times I, that's the imaginary part. Just like I hope you would expect them to be. Just treat them like binomials. Combine like terms. Okay? Now, once you get to doing that, these are all features that you have to have legitimate sets of numbers. The other is an additive identity. In the complex number system is 0. Okay? Because when you add any complex number to 0, you get the same complex number. So 0 doesn't have an imaginary part, or 0 an imaginary part as well. Furthermore, the additive inverse of this, that's any number that you would add to another complex number to get 0, that would be minus a minus bi. Okay, and sure enough, that's what the additive inverse of the complex number a plus bi would be the opposite of a plus bi, the negative of a plus bi, and that would be minus a minus bi. Why? Because when you add this to that, you get a minus a is 0, plus b minus b, 0i. So that's just 0. Okay? So that's your additive inverse. Just like it was in binomials, just like it was in any real numbers. Just negate it, and that's the additive inverse. All right. They've already done the math for you here, so we'll just look at it. 4 plus 1. Well, they started it anyway. 5. Say again? Plus I. 5 plus I. Perfect. We'll just skip through the chase here. I wasn't going to do any of these, but 5 plus I. Okay? How about this one? 4. 4. Okay? You add two complex numbers together, you may wind up with just a real number. Or you may wind up with just a complex, a pure imaginary number. Okay? All right. Don't sweat this. You're not going to be tested on it, but just get to know it. Okay? Here's what, ooh, goodness. What are we doing here? Now, how I would do it is exactly how they started it. If I were dealing with a bunch of binomials, I would clear the parentheses first. That would be 3i plus 2, perfect, minus 3i, perfect, minus 2, perfect, minus 5i. Okay, then guess what we would do? Combine like terms. The only two real parts I see here are plus 2 and minus 2. Guess what that adds to? 0. And the imaginary parts that I see here is 1 positive, 2 negative. 2 negatives add to be negative 8i plus 3i is, well, let's do it this way. Plus 3i minus 3i is 0, so it's minus 5i is your answer. It takes them a while to get there, but there they got it, minus 5i. So you can't have the pure real number or a pure imaginary number as an answer to adding or subtracting real numbers. Oh, here's another one. Okay, do the same thing. 3 plus 2i, that just writes down. Distribute here, plus 4 minus I, perfect. This would be a minus 7 minus I, okay. Let's do the real parts first. Well, we'll do Asia first. No, you're here. There you are. All right. Anyone else sneak in while I wasn't looking? Okay. Okay. What you do is combine the real parts. I see 2 positive real parts. 3 plus 4. That's 7. Minus 7 is 0. I see 3 imaginary parts. 1 positive, 2i. 2 negatives, minus I, that would be minus 2i. 2i minus 2i is 0. You got nothing, folks. Okay? All that, and you wind up with 0. Okay. Now, many of the properties of real numbers are valid for complex numbers as well. Associative properties of addition and multiplication. Doesn't matter how you group them, they still add or multiply the same. Funny, we haven't even done multiplication yet, and they're talking about it. We'll get that next. Commutative properties of addition and multiplication will work too. That means A plus B plus BI plus C plus DI is the same as C plus DI plus A plus BI. Doesn't matter for addition and multiplication what order you multiply or how you group the adding or multiplying. Distributive properties, okay? If you have something on the outside like a 7 times 3 plus 2i, then multiply 7 times this and 7 times that. Yeah. Distributive property works. Distributive property of multiplication over addition. All those work just as before. Okay, and we actually were doing some last time. Oh, and what do we have here? Multiplication of two real complex numbers. Notice how these properties are used when two complex numbers are multiplied. Guess what? I really don't care about those. I just want to, guess what I would say do to this. It's like multiplying two binomials. And what do we call that? Foiling it, of course. So A times C, that's your first. Okay, they go through all this. So that gives you AC. Then you have a ADI plus BCI. Okay, sounds like a company, doesn't it? Okay. And then the last is plus BDI squared. But what in the world was I squared? -1. So that would be a minus BD. That's the only new part here. It's actually easier than multiplying any other two binomials. Okay, here's Hamina. All right. Anyone else come in? Oh, I wasn't looking. So, basically, you got AC minus BD. There's your real part. Your imaginary parts, AD plus BC times I. So it's really easy to do. Just FOIL it. You don't have to worry about distributing and all this other stuff. Just FOIL it. It works. Just remembering that I squared, when you FOIL this last term, BI times DI, that's BD times I squared, but I squared is -1, so that's a minus BD. That's the only new part. So guess what? Usually when you're FOILing two binomials, you come up with a 3-term polynomial. Here you only come up with 2, a real part and an imaginary part. Okay. Now, rather than trying to memorize the multiplication, simply remember how to use distributive property, or even simpler, FOIL it. Just FOIL it. Don't try to memorize a package here. Just FOIL it, and you got it knocked. Okay? Any questions? And again, you're not going to be tested on this, so don't get panicky about this or anything. Just be used to it. All right, let's do this quickly. This is distributive property. What would that be? -8 plus 12i. There's your answer. You can do all these steps if you want to, but it's just right there. Okay? How about this one? Ooh, boy. That would be what? 2 times 4 is 8. Hang on to that. Now, because we know what it's going to be on that last term, let's jump to the last term. Let's not spell FOIL correctly here. The last term will be, say again, minus 3i squared. And what's I squared? -1. So that would be times 3 is, times -3 is +3. So you have 8 plus 3 is 11. You can go straight to the last term and get your other real part. So hang on to that, 11. And then you do the cross terms. The outer is 6i minus 4i would be 2i. So what do we have? 11 plus 2i. Is that what we wound up with? Let's see. They're going to do it and do it and do it. Ah, there it is. 11 plus 2i. Now, take all the steps you need. If you want to go through and do it the way they do, do it. It works, okay? But if you want sort of the shortcut, just remember the real parts are the first and the last. And then the imaginary parts are the inners and the outers. Okay? Make sense? All right, want to do that one? 9. Negative 4 times minus 1.
Yes.
Which is? Positive 4. So 9 plus 4 is 13, right? Okay. Oh, wait. We didn't do the inner and outer, did we? What's the outer? Minus 6i. The inner is? And what do those add to? 0. So we had it to begin with. 9 plus 4 is 13. Whoa! That was too easy, wasn't it? Now, what did we have here? Let's take a look at this. We're jumping up a little bit. Here we have the sum times the difference of the same two parts, right? I don't know if you remember what we call this. We call this a conjugate.
Yep, the conjugate.
A plus b times a minus b. That's a conjugate. When you were trying to rationalize denominators with irrational numbers, multiply by the conjugate. It would work. Here, if you multiply a complex number by its conjugate, you get a real number every time. Every time. Because these two cancel out, add to 0, and these two are going to be real numbers. And it's always positive, by the way. Okay. So that turns out being 9 plus 4 is 13. All right, good deal. Oops, here's one another. You think this will produce a real number? No, it won't. Because split this up and then FOIL it. 9, let's go to the last. 4i squared, which is? That'd be minus 4, right? 9 minus 4 is 5. There's the real part. Now let's do the imaginary part. 6i plus is 12i. So what do we have? 5 plus 12i? Yeah, that's what it is. Pretty straightforward and easy to do. Okay? Finally, they got there. 5 plus 12i. Yeah, two things to remember with complex numbers. I is the square root of negative 1, so therefore I squared is negative 1. Two things to remember. That's it. It's sort of like f of x is always y, okay? So square root of negative 1 is always I, and I squared is always negative 1. Okay. And now they choose to talk about complex conjugates. We just did so, okay? If you notice in 2c, which we did notice, the product of two complex numbers can be a real number if those two numbers are complex conjugates of each other, or multiples of complex conjugates of each other. That would work too, but we aren't getting into that yet. So let's do it with letters rather than numbers. They're so much easier, aren't they? Okay? If you multiply a plus bi times a minus bi, those are complex conjugates of each other. Just conjugates of each other. They just happen to both be complex. The first is a times a is a squared. There it is. The outer is minus abi, and the inner is plus abi. Those add to 0 every time. Okay? Go to 0. And so you go to your last, and that would be minus b squared, I squared. But what's I squared? Minus 1. So minus b squared times minus 1 is plus b squared. So it's a squared plus b squared. Now, this is sort of a stretch, but remember we used to say you can never factor the sum of two perfect squares.
Right.
Not with the real number system.
Oh.
But now that we've got complex numbers, you can. Okay, but not that we're going to, but you can now. This opens up and says, so never say never. Okay. It may be you can. All right. Now, this leads to to dividing complex numbers. Oh, my word. Remember how bad, well, long division was sort of bad anyway, wasn't it?
No.
But if you had decimal numbers that had big, long pieces to them, you had to move decimals and all that kind of stuff. You had to get Tyra here. You had to do all sorts of things like that. And there you are. All right. It is turning out to be a fairly well-attended class after all. Okay? But then, when we got to irrational numbers, oh, those were impossible, because irrational numbers, you can't write as rational numbers, you can't write as fractions. You always just estimated those. So they got really hairy to do long division. That's why we rationalize the denominators. How? By multiplying by the conjugate. Okay? Well, guess what? We'll do the same thing here. 3, right? No. Yeah, sorry. I can't find you. I know you're in here. Alana, is that right? Huh? One more time. Kiara. Okay. Kiara, I got it. Okay, sorry about that. All right, anyone else come in? Okay, sorry. All right. So this time, if you're trying to divide, how can you divide by an imaginary number? Well, I don't know. I mean, I have trouble enough dividing by whole numbers, okay? Okay, so how do you do it? Well, if you don't like having an imaginary number in the denominator, we can always multiply by the conjugate and it becomes real, right? But if you multiply the denominator by that, you also have to multiply the numerator. Not the conjugate of the numerator, but the conjugate of the denominator. Multiply that. Because what's C plus di, C minus di over C minus di? It's 1, right? Okay. So you can multiply by 1 anytime you want to. Okay. So this time, the numerator gets a little worse. Not bad, but a little worse. A times C would be AC. Now let's jump to the complex parts. Plus BI times a minus DI would be a minus BD I squared. What's I squared? -1. So that would be a minus DI BD minus 1 would be times a minus 1 would be a plus BD. So there's the real part. The imaginary parts are your inners and your outers. That would be minus ADI plus BCI. So BC minus AD times I. There's the imaginary part. Okay, that got a little more complicated, I admit it. What does the denominator become? C squared plus D squared. That's what happens when you multiply by the conjugate. Okay? And that's now a real number. And you can divide by real numbers. Whatever this is, divide it by that. Whatever this is, divide it by that. And you have your complex number in standard form. And I won't work it out, but let's just talk through it. Okay? Here's division by complex numbers. Ooh, yuck, I don't even know how to do that in long division. Okay? So what do? Multiply by the conjugate of the denominator. Both in the numerator and denominator multiply with that because that's 1. Okay? The numerator becomes 8 minus 6, because the I squared is minus 1. 8 minus 6, that'll be 2. Hang on to that. And then your complex, your imaginary parts will be 4i plus 12i would be 16i. So what do we say? 2 plus 16i. That's the numerator. Okay? And what was the denominator? 4 squared is 16 plus 4. Well, 4i times 4i, I mean 2 minus 2i squared times positive 2i squared is minus 4i squared. I squared is minus 1, so it's plus 4. 16 plus 4 is 20. All right. So what do we have? We had 2i plus 14 all over 20. Okay? Let's see. It takes them a while to get there, but let's see what they get. 2 plus 16i over 20. Now, okay. The problem here, this isn't quite in standard form. So what we do is split it and do 2 over 20 plus 16i over 20. Well, 2 over 20 is 1 over 10. That's a real part. And this will be, 4 over 5i plus 4/5 i. So 1/10 plus 4/5 i. That's written in standard form. 1/10 plus 4/5 i. Aren't you glad we're not going to have to do many of these? In fact, any of these. But they're easy. It's not that bad. Okay, everybody got it? Okay. Again, you're not going to be tested on this, but in case you ever need it to know it, it's there. Oh, it might be something very valuable. Okay. Any question? Oh, what did it? Okay. I'm sorry. I asked the wrong person if it was valuable. Okay. Everybody got it? Okay. Now, why are we even messing with this? Well, sometimes quadratic equations wind up with complex solutions. Now, before we do that, if we have a quadratic equation, okay, what's our standard form for solving? Okay, ax squared plus bx plus c equal 0. That's the standard form for a quadratic equation. And if you have any other kind of equation, quadratic equation, get it into that form. Then what do we do once we have it there? You either factor it if you can, but if you can't factor it, quadratic formula. You remember how that looks? B minus B plus or minus the square root of B squared minus 4AC all over 2A. Here's the kicker. That thing that's in the square root there. If that ever came up negative, then you need complex numbers. Okay. If it came up positive or 0, fine, you have your solution. But if not, you have complex solution. So that's what's going to be happening. Now, you can write a number such as square root of negative 3. How would you write that? Yes, that would be the square root of 3 times the square root of negative 1. And what's the square root of negative 1? I. So this will be square root of 3 times I. Now, the book always writes it in standard form with the I afterwards. I don't really like doing that in this case because sometimes my lines are a little sloppy and I can't tell if the I is inside or outside the house. So what I like to do is put the I in front. That way there's no mystery about it. You know it's not standard form, I admit that, but it's easy to read and easier not to make a mistake. But they're always going to do it and do the square root of 3 times I. And they write it so close together, you have to really look hard to make sure you don't misinterpret. When I'm writing up here, it's going to be easy to misinterpret. Okay? So the number square root of 3 times I is called the principal square root of negative 3. Okay? So, what is the principal square root of that negative root? When a is a positive real number, the principal square root of negative a is defined as the square root of negative a would be I times the square root of a. Okay, I just don't like writing the I at the end for square roots, just because it's really easy to confuse. But square root of a times I. Again, nothing you have to be responsible for, but just knowing it. All right. I'm not going to do this, but do you think you can factor that? No. Okay. Because this is a prime number, its only factorization is 3 times 1. This is a prime number, its only factorization is 5 times 1. No way you combine 3 times 1, 3 and 5 in any way whatsoever and get a 2. Especially a minus 2, because this would be a minus 5 times minus 1. It's not going to happen at all. Yeah. So this is going to produce a non-factorable form. So quadratic formula, here we come. And there we plug it in. The b is minus 2, so minus a minus 2 is positive 2, plus or minus negative 2 squared, minus 4 times a times c, minus 4 times 3 times 5. Can you already see what's going to happen? And 2 times 3 in your denominator. Whoa! This is a small number, but positive, because it's squared, always squared. These, both of those being positive, that one's always negative. That's going to be a big negative number. You wind up with a complex situation. Now, what you do here, if you remember back to radical expressions, always pull out a perfect square. Okay? Do you see any perfect squares in here? 56. 4. 4 times 14, I believe it is. 4 times 16 is 64. 4 times 14. 14 doesn't have any perfect squares in it, so you can pull out a 2. Square root of 4 is 2. But the square root of negative 1 is square root of negative 1? I. So I would pull out a 2i, okay? And that leaves the square root of 14. Well, then 2 will go into 6 3 times. 2 will go here, 2 will go there. So you have 1 plus or minus I times root 14 all over 3. You can split those up if you want to. And that's what they do. They factor out the 2, and they put the I at the end. Okay. And that would be 1/3 plus or minus root 14 over 3i. Now that's a little bit better this way because it's a lot easier to tell the I is not under the radical. This is hard to tell. That's a lot easier to tell. But I still like to put the I in front. Okay, I'm just stubborn. Okay. And that's it for 2.4. Again, no homework. Nothing you have to do on it, just to get you exposed. Do you feel exposed? Are you now infected with complex numbers? Yes, you've been exposed to it. So let's go on and end this and go on to 2.5. That's where we wanted to be, isn't it? All right. Boy, it's warm enough in here, isn't it? Of course, my wife said, "What are you doing wearing a flannel shirt today?" I said, "It's in the 40s outside." But she said, "It's going to get in the 60s. I said, "Well, I can take off my T-shirt." But, yeah. Okay. All right. Wasting class time doing this, but I'm hot. Okay, so let's go to current slide. We're rapidly coming to the end of chapter 2. Not quite there yet, but we're still in chapter 2. Polynomial and rational functions. We're still in the polynomial part. This is the last section of the polynomial part. We're going to do zeros of polynomial functions. Remember, way back, I think in section 2, so one of the most important things that you can do with polynomials is find the zeros. So we're going to start trying to. Okay? We'll use the fundamental theorem of algebra to determine the number of zeros of a polynomial function. Okay? We'll find the rational zeros. Ha! Those will be fun. Then we'll find conjugate pairs of complex numbers. We're kind of going to skip that. I'll show it to you, but you won't be responsible for it. And then we'll find the zeros of polynomials by factoring. Okay? And guess what part of that factoring will be? Synthetic division. That's why we did that. We'll use Descartes' rule of signs to determine how many possible positive and negative zeros you have. We'll use the upper and lower bounds to find when you can stop looking for zeros of polynomials. And we'll find zeros of polynomials in some real-life applications. Yes? Go back? Oh, I'm sorry. Oh, you didn't want to go back? Oh, this one. Okay. Yeah, I'll leave it. I thought you wanted me to go back to one. The other thing to note today, one of the reasons we're sort of a small crowd, probably a baseball game today because all four of the baseball guys are out. Okay. And they're usually here.
Don't they have conference this week?
What's that?
They have conference this week, don't
they? They have, oh, conference, yeah, yeah. And they are one of the better teams, so I bet you they'll be in it for a while. Yeah. Is that, and
We've
that's...
had a good season so far this.
What's that?
We've had a good season.
Yes, very good, yeah. And you're a part of it because they were in your class. Four of them anyway. Okay. So let's look at the fundamental theorem of algebra. Okay. There was a incredibly brilliant German mathematician named Carl Friedrich Gauss. Oh, that could be a paper topic, couldn't it? Hint. Papers. Research papers. This is time for a little advertisement. In this, one of my best classes ever, of course, I've had 1, 2, 3, 4, 5, 6, 7, 8, 9 papers turned in. Isn't that wonderful, except that we have 35 students in here, okay? It's not quite, I mean, it's a good that y'all have turned it in. Please get the rest of them. Oh, what's coming up next week? Spring break. You got 5 days to work on a paper. All right. Well, how wonderful. Okay. And I think most of you have a quiz you can work on too. Huh? Yes. Okay. Speaking of quizzes, the first quiz, I have all but 1, 2, 3, 4, 5, 6. Still 6 people haven't done the first quiz. That means at least 6 people haven't done the first test either. Hey, we're getting near the end of the term. Get those quizzes done. Spring break's a great time to get those caught up. And mentioning that, the first test, if you look on Blackboard, if you see a score there, that means I thought you were finished. If you don't see a score, but you did work on it, that means I wasn't sure if you're finished or not. So let me know so I'll know whether to put that score in or if you're going to work on it some more. Okay? And then quiz 2, you just got recently, and I'll give anyone who didn't get a quiz 2, pick up one before you leave today. All right. That was enough of the paid political commercial. Okay. Now, in the complex number system, every nth degree polynomial has precisely n zeros. Now, I don't know if you remember me saying it before, and I think we had it on the slide. If you have a polynomial there, you can look at the degree of it, and you'll have no more than that many zeros. You may have less, but you can't have any more. This says if you count the complex zeros, you'll have exactly n zeros. Okay? Exactly, precisely n zeros. Okay. That important result is derived from the fundamental theorem of algebra, first proved, or proven, I'd say, by the German mathematician Carl Friedrich Gauss. Really brilliant mathematician. I think he, and he was a great scientist as well, he and a guy named Euler probably were 2 of the most productive mathematicians of all time. I mean, his number of papers and things like this published, unbelievable. You think, when they have time to eat, you know, they were publishing so much. Gauss was also quite famous as a scientist as well, and it's hard to separate science from math, but the unit for magnetic field, the original unit, was the Gauss, named after him. Okay? He's all over the place. when you do linear algebra, you do Gaussian elimination. All over the place, okay? So, fundamental theorem of algebra states that if f of x is a polynomial of degree n, where n is greater than 0, of course, a polynomial of degree 0 would be a constant, okay? That's not very interesting, okay? So, of degree n, where n is greater than 0, then n has at least 1 0 in the complex number system. Well, that's a really lame definition, because the complex number system is all numbers in the world. Okay, so that means it has at least 1 0. And this says it has precisely n 0. Whatever n is, it has that number of zeros. Okay? So, using the fundamental theorem of algebra and the equivalence of zeros and factors, remember we said that before too, you obtain the linear factorization theorem. If f of x is a polynomial of degree n greater than 0, of course, then f of x has precisely n linear factors. So you can break this if f of x has a polynomial of degree n, a sub n, that's just some coefficient in front, x minus c1 times x minus c2 times x minus c3 times all the way down till you get whatever n is, x minus cn. Exactly n linear factors. Now, keep this in mind. Two things. One, the c's here are used because that means they can be any complex number. But remember, all real numbers are complex numbers too, right? Just have the imaginary part 0. The other thing to keep in mind, the c's could be 0 themselves. Okay, that's fine. And you can use the same c several times. Remember when we had multiplicity of 3 or something like that? So this one and that one could all be 7 or something like that. So you could have multiplicity. But they can be written this way, where c1, c2, up to cn, exactly the same number of roots as you have degree. Those are complex numbers. They could be reals, because real numbers are complex, and they could be duplicated. So 3 of these could be the same thing. 7 of them could be the same thing. 2 of them could be the same thing. And some of them could be 0 as well. Okay. Note that the fundamental theorem of algebra and the linear factorization tell you that not only are the zeros of factors of polynomial exist, but they don't tell you how to find them. Okay? Yay, well thanks for telling us that. We need to know how to find them. So these theorems are existence theorems. They're not how do you solve the problem helpful. Okay? They just tell you they exist. Okay? Yay. So, here's what's the degree of that polynomial? 1. Maximum exponent is 1. How many zeros does it have? 1. Because that's its degree. And you happen to know what it is? What zeros it has? Set that equal to 0. X minus 2 is equal to 0. Add 2 to both sides. X equals 2. All right? It has one factor. Okay? Exactly one factor. Because the degree is 1. X equals 2. Boy, that was a hard one, wasn't it? Especially since they did it for you. Okay. Now, counting multiplicity, this second degree polynomial, oh, they haven't done the answer. How would you approach that one? Okay, first asking, how many zeros does it have? 2, because the maximum exponent is 2. So it has how many factors? 2. Okay. Now those zeros may not be real numbers. They could be complex numbers, imaginary parts. Okay. So what would be your first approach? Factor it. Good choice. Say this again. Well, yeah. Set it equal to 0 first, and then factor. Yeah. Okay. Does it factor? How? X times x, minus times minus, 3 times 3. Perfect. Okay. Now, because those two factors are identically 0, this has 2 roots, or 2 zeros, that just happen to be the same number. Okay. So you have x minus 3 is equal to 0, or x minus 3 is equal to 0. This is really creative, isn't it? Add 3 to both sides, add 3 to both sides, and you get x equal 3, and or my other brother, x equal 3. Okay. Same number, but we count those as 2 zeros because it's a multiplicity of 2. So that's 2 roots. They just happen to both be the same number. Okay? Now that's how we did it. Let's watch how they did it. Oh, you still writing? Okay. So you count your multiplicity when you're counting your zeros or your factors.
So that will show you the multiplicity shows you how many turns your graph would have.
No, the turns of the graph would be one less than this.
Okay.
Up to that many. You may not have that many.
Oh, yeah.
Number of zeros, you have exactly that many, but that has a count complexity. We have them, but they're two of them, both of them are the same number. Now, what that tells you, the multiplicity, if you're thinking back on that, if the multiplicity is odd, that means it crosses the x-axis. If it's even, it kisses the x-axis and goes back the same way. Okay. Or it could be like that too. Okay. So, all right to erase? Some people still writing. Okay. Okay. So let's see what they do. Well, they didn't even set it equals 0. Shame on them. But they factored it and came up with 2 zeros, even though they hadn't set it equal to 0. And that's called a repeated 0 multiplicity of 2. They really needed to because they're not zeros unless you have an equal 0 out there. Okay. All right. How about that one? Oh, my goodness. What will you do first? Same answer as before. What was that? You do what? Factor. And what do you factor? X out. And what are you left with? X squared plus 4. Guess what? 1 real 0 and 2 complex zeros. Because this cannot be factored. This will not equal 0 in the real number system, but in the complex number system it will. So the only real 0 here is, you set it equal to 0, sorry, and then x equals 0, or x squared plus 4 equals 0. And remember, we can't do that in the real number system, because if you subtract 4 from both sides, x squared in the real number system can't equal a negative number. Complex, it can. Plus or minus 2i, but you're not responsible for that, huh? No, no such thing. No, what is it?
I think I just my own question. So I know when it's like that at the end, we usually set each.
Yeah.
One equal to 0 like this.
Yeah.
Oh, that's what you mean.
Yeah.
Okay.
And then I said this is equal to 0. That's a 0. It is 0 and it is a 0. Okay.
So
this one. What's that?
You want to try to undo the square root?
Okay. If you do, yeah, x equal negative 4. X squared equals negative 4, right? Okay. Can you try to take the square root of negative 4? You can now, but you couldn't before. 2i, plus or minus, yeah. You can't in the real number system, but you can in the complex. I'm not going to have you do those, okay? But you know how to do it now if you needed to. All right. Now they're going to do it, so I'll let you see them do it. It'll be perfectly fine. But first thing they did was factor before they set it equal to 0. Shame on them, okay? And then they factored the x squared plus 4 into x minus 2i times x plus 2i. Now, we haven't done factoring and getting complex numbers, but we could have done it the way we did. It has exactly 3 zeros, 1 real 0, 2 complex zeros, 2 imaginary zeros. Actually, you should say it has 3 complex zeros, because 0 is also complex. Okay, these are 2 zeros with imaginary parts. Okay, now I'm going to point something out to you that's coming up later. Okay? Whenever you have a zero that is imaginary, guess what? Its conjugate is also going to be a zero. Okay? If this polynomial had real coefficients, which they do, then if you have one imaginary part, you have another one. They always come in conjugate pairs. Always. Okay? So this is 0 plus 2i and 0 minus 2i. Just 2i minus 2i. Those are conjugate pairs. They always show up in pairs. They're never alone. Okay? Real parts, they can be singles or doubles or whatever. Okay. Now we get to the how-to part. Well, let's see. They just skipped example 2, didn't they? No, we haven't gotten there yet. Okay. I was going to say. Rational zeros test. Remember, the others were existence theorem. Now we're going to deal with how do you find the zeros. Factoring will do so far. Sometimes you can't factor. And if it's bigger than a quadratic, you can't use the quadratic formula on it. So here's a rational zeros test. Okay? They like tests, don't they? It relates to the possible rational zeros of a polynomial having integral coefficient. That's the key here. Okay? If you have integral coefficients, you can use the rational zeros test. So far, I don't think we've had any polynomials with decimal or fractional coefficients. Maybe we've had a couple of fractional coefficients. But for the rational zeros test to work, these have to be integral coefficients. And most of them have been. Now, relates finding the possible zeros not to all those coefficients, just to the leading coefficient, that's the one of the maximum exponent, and the constant term, the one at the end. The one at this end and the one at those ends. The other end. Okay. So here's what the rational zero test is. If this is your polynomial, let's write it in letters so it's real easy to see, right? Okay. F of x equals a sub n. That just means it's the coefficient that goes with x to the nth power. Okay? Plus a sub n minus 1 times x to the n minus 1. This is just the coefficient that goes with that one. Plus, and you step all down until you get a sub 2 times x squared, plus a sub 1 times x, plus a sub 0 because it doesn't even have an x with it. Okay? Now, if all those a's are integers, not fractions, not decimals, integers. Positive or negative is fine, but integers. Then every rational zero of this function has this form. Some sort of form of p over q. Okay? A rational zero. P over q. Ratio of two numbers, integers. Of course, q can't be 0, of course. Where p and q have no common factors other than 1. So if they have a common factor, factor it out. Okay? Okay. No common factors other than 1. Now, what is your p? Your p is some factor of this a sub 0. And what's your q? That's some factor of your a sub n. And remember, a sub n can never be 0, because if it was, that would be a 0 term here. This would be n to the n minus 1 polynomial, not a degree n. So a sub n can't be 0. So therefore, you can divide by that. So all the different factors there. That's it. If you have a rational zero for this, it's going to be of that form. Now that's the blah, blah, blah version. Let's see how it really works. Okay? To use the rational zero test, you should first list all the rational numbers whose numerators are factors of the constant term at the end, and whose denominators are factors of the leading coefficient, the coefficient at the beginning. So all your possible ratios, rational zeros, are factors of the constant terms divided by factors of the leading coefficient. Having formed that list of all the possible rational zeros, use a trial and error method. Oh boy, we'll perfect that. Trying to make the fewest number of errors and fewest number of trials then too. Method to determine which, if any, are actual zeros of the polynomial. You're always going to come up with a whole bunch more than you could possibly use, so you have to find out which ones, if any, work. Note that when the leading coefficient is 1, that denominator becomes really simple, okay? Because all the possible factors of 1 is 1, okay? Plus or minus 1, but it's still 1, okay? So then it's all the possible factors of your constant term, okay? So here's 1. Now this is example 3. They're skipping example 2, so let us do example, get out of there, example 2 first. Okay? Oh my. Do we have time to do example 2? I think we do. Okay. F of x is equal to x cubed plus x minus plus 1. Okay? Now, yeah. Okay, that's your polynomial. So, I can't factor that, okay? So, let's go to the rational zeros test. The rational zeros will be of the form P over Q, where P are all the possible factors of 1, which is pretty simple. That's plus or minus 1, okay? And the Q is all the possible factors of 1, okay? So that's going to be plus or minus 1. Okay, I can list them all. They're either going to be plus 1, plus or minus 1. That's it. So let's see if any of those are. Plus 1 is really easy to check. Because when you put a 1 in for x, that's just 1, and that's 1. So 1 plus 1 plus 1 is 3. That's not 0. Nope, not going to work. Negative 1 is a little harder to check, but we can still do it. Negative 1, plus 1. Negative 2 plus 1, negative 1. No rational zeros. None, not a 1. So that was a sort of bad one to start off with. You say, well, this test doesn't work, does it? Yes, it does. It's just this one doesn't have any. Now, let's put on our thinking caps about what we already know. This is a cubic polynomial, meaning the end behavior is like this, isn't it? Okay? So it has to have at least 1 0. Okay? It's just not going to be rational. And when you see the picture in the book, you'll find out it only has 1. It's an irrational number. Okay? We can't find it using this test. Okay? Now, you say, where are the other 2? Complex. Okay? Because it only crosses the x-axis once. That's your real zeros. The others are complex. Okay. There is a checkpoint there. Please do the checkpoint as soon as you can after class. Okay. Now we're ready for example 3, but I don't think we have time for it, do we? Okay. Let's see if there's enough homework exercises you can do, perhaps, to do. I don't know. We didn't get much done in this section. You can do either any of the odds 9 through 13. Sorry, I can't breathe. They're all at Calc Chat. 9's at Calc View. And it says you can use the rational zero test to do 15 or 17. They've drawn the graph for you. I would say, let's wait till we do more the next example. So not a lot of homework here. Sorry about that. You can do all the homework you want to in 2.4 if you want to do that and catch up on other homework. But I would say let's get your papers done and get your quizzes done and get ready for that first test if you haven't done it. Now, is anyone here who did not get the first quiz? I know there's at least one person. No, I'm sorry, second quiz. Oh, look at this, another paper coming in. Something for me to do over spring break. Thank you very much. Okay. All right. Anyone does not have quiz 2? Before you leave.
Put on a big pen.
Okay. Quiz 2? Need graph paper?
No,
Huh?
sir.
You
No,
don't?
sir.
Okay. Need quiz 2?
Thank you, sir.
Huh? Did she check or something? She never knows.
She just asked me.
Okay. Does she need graph paper or do you know? Okay, thank you. Okay, thank you so much.
I know you can keep me, but I have.
Okay. If you go back to the first quiz, remember when we talked about translation? Yeah, that's what we're talking about here. Horizontal translation, vertical translation, stretches, shrinks, reflections, that's what it's talking about. Okay.
I need my second.
I thought so, yeah. And do you need graph paper? Okay. Need graph paper? You want a second quiz? Huh? Okay, do you need graph paper? Huh?
Yes, sir.
Yes, okay. Okay. Anybody else need second quiz? Everybody got it? I do need to turn off the recording.